Okay, thank you, Hideo. So our first speaker is going to be Professor of Applied Physics, Amir Safavi-Naeini. And go ahead and hand you the mic here.
Yep, I can. Okay, can everyone hear me? Great. Okay, now I have to connect the. So first, it's very early in the morning for me, so this is. Marty is fact checking me. Okay. I think I shared it, but is this working? Okay. So now I have to find the right window. Okay. That's it. All right, this is sort of weird. Let me get this. Oh, there we go. Okay. Okay, great. So thanks for organizing this, and thank you, Jonah, for all your work last few weeks. There's been we've had a lot of workshops now with QFarm. I'm Amir Safavi-Naeini. I'm going to talk about a little bit about how strong we can get parametric interactions in both the circuit platforms and the optical platforms. And this is the first talk. I won't take up the whole hour. I want to leave some room for discussions. And I'm also this is actually a talk that I prepared for this workshop. So it's a little bit of a tutorial just to create a common language, especially given that there's people from different fields. So, I hope there's something new for everyone. But yeah, it's going to be at a different level than a normal talk that I would give. So, so to start, the fundamental question that we're trying to answer here is how strongly can we make quantum systems interact? And this is an important question if you're trying to, for example, build a quantum computer where the speed of these interactions determine how quickly you can do your gates or your measurements. And it's also important if you're trying to build quantum networks, the rate at which you can generate entanglement has to do with the rates of these parametric interactions. So in general, these rates always need to be compared to loss rates in the system. And when, this is actually a very general and very kind of broad problem. There's basically 3 layers that we can consider. So one of them is just like the laws of physics. There's a fine structure constant, there's speed of light, there's impedance of free space. These set of limits on interactions between different systems. These are sort of our hard limits. Then there's the laws of economics. So what materials can we actually work with in the clean room? What are we allowed to build? What wavelengths are convenient to work at? What temperatures can we operate at? What elements are easy to fabricate? Everyone, for example, in the microwave world, for their strongest interactions, they use aluminum oxide, aluminum junctions. That's because they're very easy to fabricate. You get a nice oxide layer that's kind of a self-terminating oxidation process, and you can start a lab and be doing that in just a few months. And then within this context of the laws of physics and economics, then we can ask, given that we're given these constraints, what are the interaction constraints that we can get? So this is sort of third layer that I'm going to try to focus on. And so even that question is a little bit broad. So I'm really just going to give you two stories that have been relevant in my life and life of the people in my lab, which are related to superconducting circuits and cavity optomechanical devices. And there's also an effort in my lab developing lithium niobate circuits. There's going to be a lot of talks about lithium niobate circuits, so I won't. Ali Reza is coming, and so I won't talk about that today. So just to create kind of the common language, especially given that there's people from the field of optics here, when we I'm going to start with the simplest possible circuit. So this is our LC resonator, and we're going to try to understand this. Usually when we're trying to do the quantum mechanics for these circuits, we introduce a flux variable. Flux is better to work with than voltage. And you can think of the flux as the position. In a system, it's a position operator. There's a conjugate momentum operator, which is the charge. And so we have this commutation relation between flux and charge. And so for this circuit, the energy is related to the charge across the capacitor and the flux through the inductor. So you have this Hamiltonian that's quadratic in the position and the momentum. And you can think of the capacitance as being the mass of this particle. This is now a one-dimensional particle. This position is the flux, and so the mass is the capacitance, and the spring constant is inverse the inductance. And now we have basically harmonic oscillator Hamiltonian. We can diagonalize it. It's convenient to introduce the creation and annihilation operators, and we can get the 0-point fluctuations for the flux and for the charge, which tell you, when this circuit is in its ground state, how much does the electric field fluctuate, and how much does the magnetic field in the inductor fluctuate. And when you set the energy of that equal to h bar omega, you get that the 0-point fluctuations for flux go as the impedance, square root of the impedance, and for the charge, it's square root of 1 over impedance of the circuit, where the impedance is square root of L over C. So this is stuff that I learned from actually Michel Deveray's notes from, I guess, well, I didn't learn them 30 years ago, but they were published 30 years ago. And you can, also in those notes, consider much more general circuits. So if I have a general circuit, I have a bunch of nodes. These nodes have some capacitances between them. We define the capacitance matrix by looking at all the capacitances going to every node and the off-diagonal terms of the capacitance between the nodes. And then you can kind of similarly define this inverse inductance matrix, which the electrical engineers call the susceptance. It's defined in this way. And each of these, and you can define basically in the same way, you can define these variables. So if I have n nodes, I have n-1 degrees of freedom, because we usually ground one of the nodes. So now you have you can think of it as n-dimensional, a particle in an n-dimensional space, or n independent particles. And the Hamiltonian is again quadratic, except it's this kind of matrix Hamiltonian. And now the capacitance is a matrix. It corresponds to kind of a mass matrix in the inductance. And the susceptance is this kind of stiffness matrix. Okay, so now we have this linear system. We have this description of this linear system. And if you our life would be much, much easier if we can talk about the normal modes. Anytime you have a linear system or differential equations or partial differential equations, you want to write it in terms of its normal modes. And so we can write down the equation for the flux, and it's basically you get that the second time derivative is equal to this, 1 over LC. And that'll give you the eigenvalues. So you can get the frequencies but it's actually not a very convenient description, because if you look at the eigenvectors, when you diagonalize that C inverse L inverse matrix, the eigenvectors, like that the transformation that diagonalizes it is not a canonical transformation. It's not a transformation that preserves the commutation relations for variables. So there's a we really want to have a canonical transformation so that the variables that we get are still kind of you can still think of them as positions in conjugate momenta. And so there is a kind of a mathematical trick. You can multiply this matrix by square root of C, and then you get a matrix which is symmetric and positive definite. And from linear algebra, we know we can diagonalize this in an orthogonal way, and so we can get a symplectic transformation that or canonical transformation that that diagonalizes this. So now this matrix, these two matrices are diagonal, so we just have a bunch of independent harmonic oscillators, and that's a useful way of thinking about these circuits. Each of these independent harmonic oscillators has a 0-point fluctuation, and you can write creation and relation operators. But what we actually care about most of the time is things that are observable, like if I have a voltmeter and I look at what the fluctuations are across this inductor, how do I describe that in terms of all these creation and relation operators? And so like if this is node 1 and 2, I care about this operator, and I can write that as this phi vector, phi k. So that's really the a lot of times what we're looking for, because a lot of times what we're doing is we're putting some nonlinear element here, and we're trying to figure out how this nonlinear element mixes these operators. So and we can, with this recipe, we can exactly do that. But I just want to maybe just to say something about the nonlinear elements. So what we've done is we've taken this Hamiltonian, this is a linear Hamiltonian, we've written it in this kind of normal mode description, and now we're going to try to add the nonlinearity. And so in these superconducting circuits, the nonlinearity basically comes from two different, essentially, there's two nonlinearities that I know about. There's three, but let's talk about two of them. There's the Josephson junctions. And in the Josephson junctions, the nonlinearity comes from Cooper pairs tunneling across the junction. And this gives us a current phase relationship, which if you express as an energy so you have a cosine of the flux across across two nodes. If I put a junction across those two nodes, we can also have kinetic inductors, and the kinetic inductor, you have basically your inductance comes from the momentum of the Cooper pairs in a sense, and when these Cooper pairs have a lot of energy, they break, and so your momentum starts to depend on the inductance will effectively depend on the current. So you get this extra term, and now I can put these elements. I can turn one of these inductors into something that's described by this slightly nonlinear thing, or I can put a junction across one of these nodes. And if I look at for example, the Taylor expansion of this cosine term, it has all these high order parts, and that's where we get our wave mixing. So a phi to the 4 can generate products of 4 creation and relation operators. If I have 2 different modes, it can generate things like A dagger A, B dagger B, and so on. Also, feel free to ask any questions.
Why did this person go in third order?
I think this is a dispersive one. This should be called the kind of optomechanical type.
Yeah, it's a radiation.
Yeah, it's radiation pressure. Yeah, it's mislabeled. Okay. So just to advertise some work that a graduate student in my group and along with Alex McKeon, who's so Taha Rajab, that is a graduate student in my group who developed a package, and with help from Alex McKeon and Sam Bunkowski, who were graduate student and undergraduate at Stanford, they actually developed a code where you can give a net list for a superconducting circuit, and it'll do all of this automatically in kind of a more general way. I didn't talk about the effects of loops and a bunch of other things that this covers, and also this you can do gradient-based optimization. So this code, for example, you might ask, how do the wave functions change, or how does the lifetime of the modes change if you change some particular parameter, like a certain capacitance, and this code SQ circuit will actually calculate those gradients. So just want to do a little plug and give time for people to ask questions. Okay, so just going back to this thing, so we have this linear thing, and then we add this nonlinear part to it, and we get usually so the cosine has a phi squared part that we have to put back into the linear part, and the phi to the 4 generates stuff like this: phi to the 4, phi to the 6, etc. And so really what we're, I don't know why I keep, okay, so really what we're trying to do is, so the problem we're trying to solve is this: we have a linear circuit that has a bunch of modes, and we're adding, let's say, one nonlinear element into this thing. And what I'm trying to find is, what is the maximum value that terms like phi a squared, phi b squared, or phi a times phi b squared, which is generated by a three-wave mixing element, what is the maximum value that these terms can have? And this was something that was derived by Mark Prachal, who was a postdoc in my group a few years ago. So the key mathematical result for this is pretty simple. It's a sum rule, and I'm just going to walk you through it. So we have this linear circuit, and I'm just going to say that this is in a box. I don't care what it is. And this linear circuit, one thing we can do is take two nodes of the circuit, and we can inject a current into it. Okay, so if I do that, I care about the impulse response, so I'm going to basically inject a current that looks like that. So it's a charge multiplied by a delta function, and this generates a displacement. And the state after the impulse, so this is a displacement operator, because this phi can be expressed as a sum of a plus a daggers, and so right after that impulse, you have this set of coherent states where these displacements are basically proportional to what we're looking for in a way, the fluctuations in flux for the different mode across that node. So K is the index for the mode, and 1 and 2 are the indices for the nodes that we're talking about. And this flux can evolve in time, and we can calculate the voltage by just taking the derivative. This is easy to take the derivative because the omegas come to the front. And now we can ask, so I can basically write down, I mean, this is just, everything's classical, so I can take the mean value of all my operators, and I have this, and in frequency domain, I take the Fourier transform of the sine, and I get something that looks like this. So, so if I look at what the impedance is looking into this circuit, the impedance is just the voltage divided by the current. which and the current and frequency domain is just Q naught because it's a delta function, right? The delta function, the Fourier transform is 1. You essentially get an expression for the impedance of this linear system that looks like this in terms of the fluxes across those nodes. And if I have the impedance, if you take the limit of the impedance at omega going to 0, you actually get the inductance when you're looking into the circuit. So now we have the sum rule that says that if you add up, so I have this linear circuit, it has a bunch of modes in it, and what I care about is the sum of the 0-point fluctuations of flux for all of the modes in the circuit across this node. That is just going to be equal to the inductance looking into that circuit. Okay, we're happy with that. Okay, so we can use this sum rule to maximize expressions that look like this. So this is a classical constrained optimization problem. So for example, if we're trying to figure out what the highest cross-care nonlinearity is, we're trying to maximize phi a squared, phi b squared. And under the constraint that the sum of the phis is this L over 2, so I can use the method of Lagrange multipliers, and so in this case, the optimal value is when when these two are equal, and so you get the maximum possible value you can have for phi a squared times phi b squared is going to be L squared over 16 times h bar omega a h bar omega b. So just as an example, in this case, let's say we have this nonlinear circuit, and then we're adding a junction to it, and we care about the coefficient, this cross-care nonlinearity. What is the value, maximum value of that cross-care nonlinearity? You can just apply this formula. And then if that inductor is actually the junction itself, if the only inductance is due to the junction itself, then there's a relation between the tunneling energy and the inductance, and that lets you get a pretty simple expression. Basically, the dispersive coupling rate, it will always be smaller than omega a times omega b over 16 times omega j, which is the tunneling rate. So that's for kind of cross-care, and kind of more generally, you have this constraint, the sum of these flux fluctuations has to equal to the inductance looking in, and then we're usually looking for some products like that. So you can kind of calculate these for the cross-care, these kind of third-order terms, processes where it's a 4-wave mixing process where you have a pump and you're generating, for example, 2-mode squeezing and 2 modes. What should the fluxes be for that? Processes like 3-wave third harmonic generation, or third order parametric oscillation. Also, you can calculate all that. So, so this was for a circuit. You can also ask, okay, I might have a more complicated electromagnetic environment. So a more complicated electromagnetic environment is still a linear system, so I can always write down an equivalent circuit for it. So if I have a transmission line like this, I can diagonalize that transmission line and get a circuit model that kind of looks like a series of parallel LCs where the C and L look like that. And now I can ask, it was probably an easier way to do this, but you can also now ask, what is the inductance looking into the circuit? That inductance is the impedance of the line times the length divided by the phase velocity. And so in this case, what it says is that if I want to put a nonlinear element here that generates mixing between the modes inside this electromagnetic system, I can always increase the interaction between the modes in here by increasing the inductance. because what matters is the inductance looking into this node, which is the parallel inductance in here, and the inductance in here parallel with the inductance of the kind of our nonlinear mixer element. But it does say that there's going to be diminishing returns. So if sure, you want to have an infinite amount of inductance here, but when the inductance of this thing starts to be larger than Z naught d over phase velocity, then you're not really gaining very much. Your interaction rates are limited by the inductance of this element, the transmission line. Okay, so just an advertisement. Actually, this result was, Mark derived this and kind of hit it in the middle of a paper on doing forward mixing between millimeter waves and microwaves. It's a theory paper, and actually Kevin Multani in my group has been developing these types of mixers. And so in this paper, what we're trying to do is develop transducers that convert microwaves to millimeter waves, and also to do things like cooling of microwave fields using a higher frequency millimeter wave bath. And so what we showed was that there's some kind of optimal circuits for doing this. And more recently, Takuma Magara in my group is, he proposed kind of the exact opposite of what was proposed here, which is actually what you might really want to do is have circuits that couple your microwaves to lower frequencies. So if you convert linearly between microwaves and excitations at lower frequencies, given that transmission lines have roughly the same Q, and the Q tells you how many wavelengths you can propagate for, and wavelengths get longer at lower frequencies, you can actually transmit information over longer distances by going to lower frequencies, which is sort of the opposite of what we had been doing previously. And there's some calculations in here showing actually that the channel capacity really does, in theory, improve when we go to these lower frequencies. So if we're trying to connect two nodes that are hundreds of meters apart, it's actually maybe better to go to 200 megahertz from microwaves. Okay, so that was my second advertisement. And happy to take questions at this point. Yes.
So I guess I'm the other half. You're optimizing the static term.
Yes, that's exactly. Yeah.
But then is it obvious that should be like how to say this? The lift parent has a deliberately weak degree of mixing parent.
Yeah.
That's kind of what makes it parent.
Yeah.
Then your optimization would make it big.
Mm-hmm.
Make it so is this maybe like a gate-centric version or a closed system-centric version?
No, that's okay. So maybe this is yeah. So that's really interesting because I come from kind of a originally an optics background, and there we're always starved for interaction, and so we're always trying to make these terms bigger. And so I'll talk about specifically for transduction why that's really important. But yeah, I mean, you're right. I mean, at some point, you don't need them to be, say, for a paramp. You still want them to be bigger than the. Yeah, maybe for a paramp this doesn't make sense, but there are still lots of places where you want to have very large linear interactions. Like if I have if I'm trying to implement quadratic Hamiltonians where I can have large beam splitters between modes, then it seems like you want to make some of these interaction terms pretty large, right? Compared to the loss rates, to have fast gates, basically. Yeah, maybe it's a gate centric.
Well, I guess maybe I'm just advertising. I know that I want the dynamical two-wave interaction, like AP dagger.
Yeah.
That's like G4 times
Mhm.
The beat, I guess, like
Mhm. So are those rates actually large enough for what people need? I thought that you still want those to be as large as possible.
the thing I don't know about parametric, whether it's with or upfront, like I think you're not talking.
Yeah. Yeah.
I don't know if big G4 is for that. I suspect it's either one or the other, but I don't know how.
Yeah, I mean, I think the maybe another way of saying it is like there seems to be this so people like to make sometimes their linear modes as isolated as possible by putting them in big boxes, and then that really drops the interactions. But you know, it gets you higher, longer lifetimes, but for smaller interactions. So I think just looking at the interactions without looking at the losses doesn't make too much sense. Yeah, I agree. Yes. Any other questions? At least for I'd say for the transducers, it's we really just want to get very large interactions, because the larger we can make those interactions, the more bandwidth we have per transducer. So for at least for this for talking this paper, we really cared about getting very large interactions. Okay. More questions? Great. So maybe I'll kind of switch a little bit and talk about optomechanics now. So these are devices that now we're not talking about microwaves. We're talking about, you know, real photons that have EVs of energy. And no, I don't. Yeah, maybe. So in cavity optomechanics, a lot of what we're trying to do is I can make that joke because some of my best friends are microwave photons. Yeah. Yeah. But yeah, others shouldn't say these things. But so we have this optical cavity, and then we have this mirror that can move, and the way to think about this is that the resonance frequency for this mirror is inversely proportional to the length of the cavity. Sorry, the resonance of the Fabry-Perot, the optical resonance is proportional to inverse the length of the cavity. And if this position of this end mirror fluctuates, you get this like plus x here, which to first order gives you omega naught over L times x. And so now you have this three-wave mixing term, which is x times a dagger a. And it's a really nice, pure three-wave mixing. It's not from any like material. It's really just from Maxwell's equation. So this is a really nice nonlinearity, and that's why optomechanical systems, they can come in all sorts of shapes and sizes and made out of all sorts of things. There's, you know, LIGO, you can think of it as an optomechanical system with a cavity that's a few kilometers long, all the way down to the devices that we're going to talk about, which are on the order of a wavelength. So this, when we quantize the mechanical system, we write it as the 0-point fluctuation multiplied by b plus b dagger, and then so we get something that's just a rate. This g naught is just a rate, and you can think of that rate as the broadening of the optical resonance due to 0-point fluctuations of the mechanical system. Okay. Now this single photon coupling G naught is usually very weak, and so this is a three-wave mixing process, so we can enhance it by reducing the order and reduce the order of the nonlinearity by putting in some pump photons. So if you do that, you get this big G which is the rate at which the optical and microwave mode talk to each other. And this gamma is basically the rate at which you can transfer information between the mechanical system and optical fields, the rate at which you can cool the mechanical system, and it's also the rate at which you can entangle, we can generate entanglement between the mechanical system and the optical system. So it's gamma is kind of a really important parameter. It's 4g squared over kappa. But there's a catch. So these photons in the cavity, so NC is the number of photons that we drive this thing with. These photons in the cavity, they cause heating. And this is especially important if we're trying to develop transducers for converting information between microwave and optical frequencies. And because these photons have to be inside the fridge, they get absorbed and they heat up the chip. And the rate of this heating is just the energy of the photons, h bar omega, times the number of photons, times kappa I, which is the intrinsic absorption rate or scattering rate or whatever loss we have in the system. So there's this really useful metric, which is the energy per bit, which is, if you take this power and you divide it by this rate, which is the state transfer and entanglement generation rate, you get a power divided by a rate gives you an energy, and that's roughly the energy you would need to do state transfer for 1 qubit or generate a Bell pair, and kind of if everything else in the experiment is working. And we can calculate what that is using these expressions, and we get that this energy per bit is basically the energy per photon multiplied by the loss divided by the interaction rate squared. Okay, so here's some, a few days ago, I just went online and tried to put together, what some of the more recent papers are in this field, and also papers from our group here, and also some of the kind of historical papers are 10 years ago. And what's really nice about optomechanics is that these loss rates, everyone talks in terms of these loss rates and interaction rates. So you can, and there's really just 2 parameters. So we can take these 2 parameters and plot them. So now I'm plotting the interaction rate versus the effective mass. The effective mass you can think of as how big the system is. So if you plot G naught versus effective mass, these papers, they fall on this kind of power law. I mean, everything looks linear on the log plot, so except this apparently is kind of all over the place. This is the loss rate versus effective mass, and this is the G naught over kappa interaction rate divided by the loss rate. Yeah, so this, at least this one is kind of striking. It really does look like it's on a line, and it has this power law where you win with m to the minus 0.62 as you go to smaller mass systems. And so, what is the reasoning behind this? I'm going to start with the easy one, which is the kappa I versus effective mass. So here it's basically, if you think of the if you think of a cavity, it's got losses that are in the bulk, and it's got losses that are on the surface. And the surface losses would scale as volume to the minus 1/3. The losses in the bulk cause a kind of constant line width. And so it looks like, at least for these papers that people have published, it's the losses scale as volume to the 1/3 because mass goes as volume. So okay, so that was easy. Then there's the interaction part. So for that, we have this expression for the G naught, and well, this is 1 over L, and this is h bar over m omega, and m is the mass. It scales as volume again. So you would expect to have like a scaling with volume, which is this kind of minus v to the minus 5/6, and it's a little bit tricky actually. You have to there's some assumptions here that if you write the actual kind of volume and surface integrals for calculating this G naught, depending on what those assumptions are, you kind of get different power laws. So for example, you can have the change in the frequency of your optical cavity could be just due to the motion at the surface, but there could also be something like a photoelastic effect, which goes as volume. So so that's what changes these power laws, but it should be somewhere in that range. And actually, what we see is within that range. I don't remember what 5/6 is, but it's a bit higher than that, and -1/2 is a little bit lower than that. So in general, this means that we're sort of the field, gets if what you're trying to optimize is G naught over kappa, you get pushed to smaller and smaller mode volumes, and the smallest mode volume that you can make a good optical cavity out of is essentially the wavelength. So so let's say we have this optical resonator. It's got a length of L and it has some cross-sectional area A. There's you can calculate the mass and the frequency of the oscillator, and we get if I try to calculate the 0-point fluctuation. Sorry, so this is actually C here is the speed of sound. I should have called it something else. But if I try to calculate the 0-point fluctuation for the motion in this thing, the speed of sound in this direction sets the frequency, and then I get an expression that looks like that. So if I plug in, for an area that's about a wavelength squared, so about 1 micron squared, density of silicon and speed of sound in silicon, which is something like a few thousand meters per second, you get a 0-point fluctuation that's around a few femtometers. And if you look at these papers, they all sort of and then we can basically, once you have the 0-point fluctuation, you can find what G naught is. So G naught is basically, the length of the cavity is on the order of the wavelength, and you plug that in and you get something between 100 kilohertz to a megahertz. And if you look at these papers, that's essentially where they are. These are very different resonators. So one of them is, in terms of length scales, the variation from one to another, it can be about 1 billion. So they're very, very different resonators. But for the ones that are wavelength scale, like in the derivation, the 0-point fluctuations, regardless of what material they're built out of, is something on the order of a femtometer. And the G naughts are all below, like on the order of a megahertz to a little bit below. Okay, so that's kind of, I think, the limit of what we can do in optomechanics. So then it becomes trying to improve kappa I by really focusing on these surfaces, and that's something this crew shown here did a few years ago. They improved optomechanical crystals, which are these devices, these two-dimensional periodic slabs, where we can localize the light and the sound. This was quite a design effort to get this to work. I personally, as a graduate student, spent probably 2 years trying to make something that could work this well, and I just couldn't get it to work. And so and then lots of people after me tried as well. So I'm very impressed by the work that Felix and Sultan and Samuel and Andre managed to do. And actually, they got the coupling rate to be so high and the optical absorption to be so low that they could get into this kind of strong coupling regime where that driven coupling rate is larger now than the line width of the optical resonator. And you can, by just pumping laser light, you get strong coupling between photons and phonons. You can generate these kind of polaritons. Okay, so that was the final advertisement. Any, yeah, right. Yeah. Yeah, they don't help. No, they don't help. Yeah, the reason they don't help is basically because so what Ryan is referring to, there's these photonic cavities where you use the boundary conditions from Maxwell's equations to get essentially a big jump in the electric field at a boundary. So you bring two dielectrics close to each other and you kind of get a localized electric field for them out. But the problem is that if you're dominated by surface loss, which is what everyone is dominated by, then the surface losses also go up. So I think you might be able to get a small enhancement by doing that, but because the losses also go up, it doesn't help a lot. So there's been a few kind of design papers and efforts in several groups to try to build those cavities, but the experiments have not been so successful. Yeah. Yeah. I know.
You mentioned that trying to go smaller volumes and reduce kappa I, right? But then the other thing, how hard you can actually
I don't. So I think that basically is what these guys managed to do. They were able to put 80,000 photons, which is a lot of optical photons, in this cavity, and which is also much more than what was possible previously. So part of that was going to a design which is sort of a two-dimensional system that also has a lot more dielectric, so that heat that gets absorbed can escape quickly. The other part was actually operating not at 10 millikelvin. This experiment was done at a few Kelvin. I don't know if any of the authors are here. Felix, 3 Kelvin. So this was done at 3 Kelvin. And then the other aspect is this kind of secret sauce part, which is how did you get the surfaces not to be annoying in this? You strip the oxide like right before, is it like an hour before the cool down or something like that? Yeah. So it's this combination of like there's some geometry operating at a slightly higher temperature, so your heat capacity is much higher and phonons can conduct better, and then and then just figuring out how to get the surfaces to behave. It's the heating, yeah. Yeah, in these systems, it's a heating issue. I think at some point you're going to hit the Kerr nonlinearity of silicon, and I think these devices were pretty close to hitting the Kerr nonlinearity. 2-photon absorption is not an issue here because these are CW, and so the intensities are pretty small. Okay, that's it's just the people who funded the work. Yeah. Yeah, right. I've considered it, but Hideo told me I can only talk for half an hour, so. Yeah. I think it's probably maybe harder for. I mean, my guess is it's just going to be make the volume smaller somehow. Make the, yeah.
There are limits on what nonlinearities one can imagine.
Yeah, I think that would be I think that would be a pretty interesting thing to think about. I agree. But yeah, and also like what are the limits of the material itself? but I don't. Yeah, I haven't thought about it. I haven't thought about it deeply, I would say. Yep. Well, if you have you can have radiation pressure in a circuit. So you can have a capacitor that, yes. There's probably other circuit nonlinears as well. I guess there's 3 that I'm comfortable talking about. Okay.
All right, let's thank the speaker one last time. So our next speaker is, well, me.